it will change the solubility. It will have an effect on the solubility. So, for example, let's consider if we had silver chromate and we were trying to dissolve it into a solution of silver nitrate instead of just pure water. A good way to think about it is to come up with the major species. So major species are just everything that could be involved in the beaker, okay? Well, we know that we have the silver chromate solid. That's a major species if we're trying to dissolve that, okay? And then what does a solution mean? Well, remember, if it's solution, if it's aqueous, that means it's dissolved in water. So there has to be some water present, and now I'm just going to save some time, and I'm just going to write H2O. I'm not going to actually draw the Mickey Mouse structure to save some time for us. But so in our solution, we definitely have to have water, because that's a part of a solution, is that it's dissolved in water. But then is the AgNO3 going to be together? No. So that is a very soluble compound. So that'll be it dissolved to its ions. So plus 1 minus 1, the ratio will have 1 silver for every 1 nitrate. And I'm just trying to spread this out around over here for everyone. Okay, and we could continue to draw more and more species if we needed to, but that is everything that's involved. So when we first put the solid into the solution, that stays as a solid. And then we have the dissolved aqueous solution, and so that dissolved aqueous solution gives us water and then both ions present. Okay? So these are all the major species present for this reaction. Well, how does that change the solubility at equilibrium? Well, we can think about it as with an ice chart. Okay? So the solid is still what we're focusing on because it's the solubility of the silver chromate. So the silver chromate will break up into the silver ion and the chromate ion. And we have 2 silvers to make that even out, okay? Now, usually when it's just dissolved in water, we would say that the initial concentrations of our aqueous on the product side are above 0. That is still true for the chromate, but it's not true for the silver ion because one of the species that's present in the beaker is the silver ion. And so since the silver ion is there, what that means is for our ice chart, the concentration of that solution becomes the initial concentration for the silver ion in the ice chart. So that's where I'm getting this number from. The 0.1 molar comes from the concentration of the 0.1 molar silver nitrate. Now, the nitrate is not important because it's not a part of the solid. So you don't include anything that's not a part of the solid into your thinking, okay? But the part of the solid that's in the ions from the solution is the important part. Okay, so then now, if we have an initial number, when we do our change in our equilibrium concentration, that's going to be a little different. Now, we're still going to add on the product side because we've got the 0 for the chromate ion. And this one, it'll be 2x because of the 2 in front of the silver. Okay? So then at equilibrium, the change for the silver will be 0.1 plus 2x, and then the chromate will be just x. Okay, well, at this point, if we were to plug into the KSP, we have 2 silvers, so remember that we're going to have to square the concentration that we plug in for silver times chromate to the first power. Okay, so if we're plugging in all of our numbers, now I told you up above that the KSP is 9.0 times 10 to the negative 12. So that's what I'm going to plug in for KSP. And then that's equal to the 0.1 plus 2x quantity squared times x. Now at this point, it looks like it's going to get pretty tough. But remember when we learned about this whole ice chart business back before? The KSP is very small, times 10 to the negative 12. So since that is very small, we can do the assumption. So when we get to this point, when you've plugged in for this common ion effect, then we can assume that since the KSP is so small, x is expected to be small compared to the 0.1, so we can do the assumption. And remember, the assumption is that you forget the added or subtracted x's. So you just like take those x's out of the equation, okay? So by taking that off, I've already done the math for you. I've figured out the solubilities. So now this is what the answer would be. If you actually wanted to solve it for yourself, pause the video, solve it, see if you get that as well. But then the first number would be if we didn't have that common ion, if we didn't have 0.1 starting out as the silver's initial concentration, if we just put in a 0, because it was just in pure water, that's what you would get. So when we compare pure water versus dissolving in a common ion solution, what do we figure out about these things? Well, we can see that the solubility is much less in the presence of a common ion, which is the silver ion in this case, than compared to pure water. The value for the pure water is significantly bigger for the solubility than if it was in that silver nitrate solution. So by seeing this, by comparing these two values and seeing how much less the solubility is in the common ion, it's good to just know in general that the solubility of a solid is lowered if the solution already contains ions common to that solid. So that's a great predictor qualitatively for you, and a way to check yourself quantitatively, that if you have a common ion, then the solubility is significantly lower. So let's calculate the solubility of solid calcium fluoride in a 0.025 molar sodium fluoride solution. Okay, so now let's figure out right away what is our common ion here. Well, for the calcium fluoride, when that dissolves, it's going to create the calcium ion and the fluoride ion. So our equation is that. So based on our two ions present when the solid dissolves, which ion is important from the sodium fluoride? The fluoride is. So this is going to tell us the initial concentration, so F0, for our ice chart. The sodium is not important because that is not a common ion, okay? Just the fluoride is the important part. So kind of forget about it, know it's in there, but it's not significant for this problem, okay? So for initially, we don't have anything about calcium, so that's going to be a big fat 0 for initial concentration. But then this is where we put in that 0.025 for the initial concentration of the fluoride ion. So then for the change, we're adding to the 0 side, and so plus x for calcium and plus 2x for fluoride. So at equilibrium, x for calcium and 0.025 plus 2x for fluorine. Excuse me. So now, again, times 10 to the negative 11, that is a very small KSP value, so we can make an assumption when we solve. So just so that you see what that looks like, I'll plug everything in first. So we've got the KSP is the calcium times the fluoride squared. So we're going to have 4 times 10 to the negative 11 is equal to x times 0.025 plus 2x whole quantity squared. So the assumption, remember what that means is you will take off any of added or subtracted x's. So the only added or subtracted x here is this 2x. So we're going to get rid of that. To simplify, so that'll now be x times the 0.025 squared. All right, and then when you solve for x, I got 6.4 times 10 to the negative 8. Okay, and this is a solubility, so it needs a unit. It's not a K. So the unit could be moles per liter or molarity. Either one would be correct. Okay. Last but not least, how do we use Le Chatelier's principle with the common ion effect? Well, we can use it qualitatively to understand the impact that the common ion has on the solubility. So if we're adding more of an ion that's already present, one of those major species, something that's already in the beaker, then the shift will be away from that species, meaning that if it shifts toward the solid, then the solubility will be lower than that of pure water. And that's what we saw when we compared back on page 12, the solubility of the silver chromate in pure water versus in a solution with silver ion. So qualitatively, we could know what the shift would be, that we would have less solubility, the solubility would be lower if you have a common ion present.